Hey, so this is going to be a video on half-lives and like radiometric dating, if you will. Not dating as in dating, but figuring out how old things are and using nuclear decay to date old substances and figure out how old they were. So let me share my screen and let's us look at screen share. We don't want to go back to the dual nature. Actually, you'll be watching that soon. I need a new piece of paper. All right, so we're going to call this half-lives and radioactive dating. All right, decay. Okay. Oops, I don't know if that video is in your way right there or not. So maybe over there. Half-lives and radioactive decay. Now, what is a half-life? It is the time it takes for 1/2 of a radioactive sample or isotope to decay. Okay. Half of it decays in a certain amount of time. That time is called the half-life. All unstable substances that decay have their own individual half-life. Okay? We could look at something like this. Down here we would have time. And up here we would have number of particles. And if this was a half-life graph, it would go like this. It would really never reach that bottom there, okay? And if I wanted to read this graph, hold on. If I wanted to read this graph to determine the half-life, let's just look at this. If this is 100 particles, well, that 100 would turn into 50, and that would be 1 half-life. Because after 1 half-life, half of it remains. And half of 100 is 50. So if I started with 100 particles and I ended at some point, I had 50 particles, without, I just lost half of my particles. So my half-life, the amount of time it took for half of my particles to decay, would be, well, let's say that's 2 days. I'll just make that up. It could be 2 seconds. It could be 2 billion years. All right, I put 2 days. Well, we also know that 50 would turn into, say, 25, right? And that would be the second half-life, right? At some point, we would have 25 particles left over. Well, that would take 4 days, because each 2 days we lose half, and we've lost half 2 times, okay? Now, eventually, that 25 would turn into 12.5. So what I see is that 25 just got cut in half. So that would be my third half-life. And how much time would it be total before we got there? Oh, it would be 6 days. Because if each half-life is 2 days, and I've had a total of 6 days, then 6 divided by 2 tells me I've had 3 half-lives. So I've had one where I went from 100 to 50. I had another half-life where I went from 50 to 25. And I had another half-life where I went from 25 to 12.5. So my original sample has cut in half 3 times to give me a total of 3 half-lives, right? We started at 100 particles. We cut it to 50 particles. We cut it to 25 particles. And then we cut it to 12.5 particles. Each time we cut in half. So that means we've had 1, 2, 3, a total of 3 half-lives, right? And we said that each half-life takes a total of 2 days, okay? So what that means is we've had a total of 6 days. All right? Okay. Now, let's look at this in a slightly different way. Let's look at number half-lives. Let's look at amount remains. Let's look at amount that has decayed. If it's decayed, it is gone. All right. Well, at 0 half-lives, let me get that out of the way. I don't know if that's on your way or not. 0 half-lives, the entire thing remains. All right. And none of it has decayed. After 1 half-life, half of it remains and half of it has decayed. After the second half-life, whether it's 2 years, 2 seconds, or 2 billion years, 25 will remain if we started with 100, and therefore 75 had decayed. After the third half-life, 12.5 will remain, and 70, or no, that would be 88.5. Actually, that would be 87.5 would have decayed. Okay, if it doesn't make sense, I'm going to try something else. Okay, let's do that chart again. Let's do number, let me pull this up, half-lives. Let's do fraction remains, fraction decay. This will probably make more sense than what we had a minute ago. All right. Well, after 0 half-lives, oops, let me get this out of the way. After 0 half-lives, the whole thing remains and none of it has decayed. All right. After the first half-life, 1/2 remains and 1/2 has decayed. After the second half-life, 1/4 remains and 3/4 has decayed. After the third half-life, 1/8 remains and 7/8 has decayed. After the fourth half-life, 1/16 remains and 15/16 has decayed. After the fifth half-life, 1/32 remains, and we have lost 31 out of 32 of our substances. Notice, if you don't like fractions, that I multiplied this by 2 to get that. I'll multiply this by 2 to get that. I'll multiply this by 2 to get that, etc. And I could have done that continuously forever. But what this tells me is if 7/8 remains, then it has undergone 3 half-lives. If 31 out of 32 remains, then the substance has undergone 5 half-lives. And if I know the half-life of the substance, I can determine the amount of time it's been around. So let's look at applying this, okay? Let's look at an example problem. Let's see, I'm going to make up an element. Element X-31 has a half-life of 653 years. How much of a 30.0 gram sample remains after, let me do a little math here real quick. Remains after 1959 years. Okay. All right, well, let's look at this. So I know that I've got a total time is equal to 1959 years. I know that I have a original mass that's equal to 30 grams. And I know that the half-life time is equal to 653 years. All right. So if I figure out my number of half-lives by taking my total time and dividing it by my half-life time, which is 1959 years, divided by 653 years, I see that I have had 3 half-lives. This substance that originally had 30 grams has undergone 3 half-lives. So what I will do is I will take my original, oops, let me get rid of that. I'll take my original mass and I'll say that after 1 half-life, right, half of it would remain, and half of 30 is 15. After the next half-life, right, half of 15 would remain, and that's 7.5 grams, right? After the third half-life, which for our case is the last half-life, we would have, make sure I do that right, yes, 3.7, should have done that one, 3.75 grams would remain. So the question says, a substance, X31, has a half-life of 653 years. If we start with 30 grams, how much of it will remain after 1959 years? And we said, well, if I take my total time, 1959 years, and divide it by my half-life time, I will see that this substance cut in half 3 times. So I'll take his original mass and I will in fact cut it in half 1, 2, 3 times until I get to the final mass. And that's my answer. So I know how much would remain. Let's do another example. Let's say if 2.0 grams of a substance with a, I'm going to pick really simple numbers, half-life of 5 minutes remains after 25 minutes. Then what was the mass of the original substance? All right, let's analyze this here. So we have 2 grams, right? Let me change that color there. We've got 2 grams remains. So our final amount equals 2.0 grams. We have a half-life of 5 minutes. So half-life time equals 5 minutes. That means every 5 minutes we cut in half. We have a total time of 25 minutes, right? And we need to know how much in original, or let's rewrite that. Mass of original sample equals question mark. Mass original sample equals question mark. Well, it looks like I need to know my number of half-lives. Number half-lives, once again, equals my total time divided by my half-life time, right? And that is 25 minutes divided by 5 minutes, which equals 5 half-lives. So I need to know the mass of my original sample. So I know that my final amount was 2 grams, right? And I know that that's just how much is left. And this was our original. And I know that whatever was in my original has cut in half 5 times. So I know that there were 1, 2, 3, 4, 5 arrows. And I know that my original must be more particles or mass, right? More particles equals more mass. So instead of cutting it in half, I'm going to work backwards and I'm going to multiply it by 2. So prior to my last half-life, I had 4 grams. Prior to that, I had 8 grams. Prior to that, I had 16 grams. Prior to that, I had 32 grams. Prior to that, I had, oh, that's my last answer, 64 grams. So I had 64 grams that underwent 1, 2, 3, 4, 5 half-lives, and I now have 2 grams. Each half-life was 5 minutes, right? So the total amount of time that passed in the process of the 64 grams turning into 2 grams was 25 minutes. Okay. Okay, let's look at another one. Let's say a sample loses 7/8 of its mass, and this is a radioactive sample, in 300 hours. What is its half-life time? Okay, so what that means is the sample loses 7/8 of its mass. So 7/8 has decayed. Well, let's look up, guys. Let's look up where we have that chart. Okay, if 7/8 has decayed, right, then we have had 3 half-lives. So I know that there have been 3 half-lives because 7/8 has decayed. So I know that I have 3 half-lives have passed. I know that the total time is equal to 300 hours. All right. So if I say the half-life time, right, will be equal to my total time divided by the number of half-lives, right? So that's 300 hours. And remember, we determined that we had 3 half-lives. So we must have a half-life time of 100 hours. All right. So we have solved for how much remains, right? We solved for how much remains in our first example, right? And our second example, we solved for how much in original amount. In our third example, we solved for, let me change my color here. We solved for what is half-life time? What is the half-life time? All right, so now let's solve for the total time. And then we could solve for the number of half-lives. Okay, so we're gonna solve for what is the total time. And that's gonna be our example problem here, okay? So let's say that I'm gonna keep it simple here. Let's say that 7.25 grams of a 100 gram substance remains. The half-life, this is how you date something, of the substance is 1,200 years. How much time has passed? Or how old is the substance? Okay. Okay. Well, we've got 7.25 grams remains. Just kind of, we have 100 grams original. We have half-life time equals 1,200 years. And we need to know the total time. So what I need is I need to first get my number of half-lives. Okay? And that's going to be equal to, well, I'm going to take my original mass and I'm going to take my final mass and I'm going to put it over here. Okay? And I'm making these numbers work for you this way. Otherwise, there's a formula. We don't need to do all that. 7.25 grams, all right? And let's cut this in half. That's one half-life, right? We're trying to get the number of half-lives. So let's see how many times it cut in half. That would give us 50 grams. Next half-life would give us 25 grams. The next half-life would give us 12.5 grams. And then the last half-life would give us our final mass, the 7.25 grams. So we have had 4 half-lives, right? Each half-life time is 1,200 years. So our total time is our number of half-lives times our half-life time, right? So our total time is 1,200 years for each half-life times 4 half-lives gives us a total of 4,800 years have passed. All right. The only thing we have not solved for is what is the half-life time. Am I correct? Nope, we did solve for that. Let's see, we can solve for each thing. How much remains, original amount, half-life time, total time, and then we've already looked at how to get the number of half-lives, okay? So It can be confusing. You've got to do the practice. All right, I'm going to go ahead and end this here. Rewatch this video again if you need to. Do them again if you need to. All right.